Ever wonder how we create these super advanced materials that power our world today? Things like scratch-proof glass or the tiny components in next-gen electronics. How do you actually build something with the perfect properties right from the molecular level? Well, the secret is in a pretty fascinating chemical recipe. Let's dive in. One of the most powerful answers to that question is a process called sol gel synthesis. It's a method for building incredible nanomaterials literally from scratch. And in this explainer, we're going to break down exactly how it all works. Honestly, you can think of the whole thing as microscopic baking. Seriously, you start with some simple liquid ingredients, you follow a very precise recipe of chemical reactions, and what you get at the end is a highly advanced, solid material with properties you designed from the very beginning. It's high-tech chemistry, but it follows the same basic ideas you'd use in your own kitchen. And just like any good recipe, this one has very clear steps. The whole process unfolds over 6 fundamental phases, taking us all the way from that initial liquid mix to the final super strong material. We're going to walk through every single one, so let's get started. Okay, our journey starts in the liquid phase. We're creating what scientists call a sol. This part is all about just mixing our molecular ingredients and getting them prepped and ready to combine. The very first step is called hydrolysis. Now that sounds like a super complicated word, but what it really means is simple. We add water. That's it. The water molecules get to work, they start breaking apart our initial chemicals, our precursors, and basically get them chemically activated and ready for the next step. Sticking with our baking analogy, this is the moment you pour water or milk into your dry ingredients, like your flour and sugar. See, you're not making the cake just yet. You're just getting all the individual components ready so they can come together. Next up, we've got condensation. So now that all our little molecular ingredients are activated, they start to connect with each other. They begin linking up one by one, forming these tiny chains and networks that are going to become the backbone of our final material. Right, so if hydrolysis was just getting the ingredients wet, condensation is when you actually start stirring the bowl. The individual parts start to lose their identity and they combine to form that uniform mixture we'd call our cake batter. And now for the really cool part. In this section, we're going to see how this liquid sol, our batter, goes through this incredible transformation into a solid structure. This big change is called gelation. It's the tipping point. It's the moment where all those little connecting networks of particles have suddenly grown so large that they've linked up across the entire container. They form one single massive network, and all the liquid is now trapped inside this new solid mesh. And you can see that transformation happening right here. We start with the liquid sol, where you have all these free-floating particles. Then they start linking up in the middle stage, and finally, boom, you get the solid gel on the right, a single vast molecular skeleton that holds the whole thing together. But we're not done yet. The new gel has to age. We just let it sit, and during this time, the chemical reactions actually keep going. The network strengthens itself, new bonds form, and the entire structure usually shrinks a bit, squeezing out some of that liquid that was trapped inside. And what's so amazing is how intuitive this is. It's just like letting Jell-O set in the fridge or letting dough rise on the counter. You're not actively doing anything to it, but the material is transforming all by itself, getting firmer and stronger over time. Okay, time for the grand finale, refining the material. We've built our structure, and now it's time to, well, put it in the oven, so to speak, to create that final finished product. And the change that happens here is immense. I mean, look at this. We start with this wet gel. It's fragile, it's big, and it's heavy because it's full of liquid. And we end up with the final nanomaterial. It's dense, incredibly strong, light, and all its internal pores are now completely empty. A total transformation. So how do we do that? With the last 2 steps, drying and calcination. First, we have to very carefully remove all the liquid from the pores without making the whole structure collapse. Then, we often heat the material to really high temperatures. This is the real baking step that locks all the atoms into a stable place, creating a dense and unbelievably strong final product. So that's the whole recipe. But you might be wondering, why go through all this trouble? I mean, what's the big deal? Well, the answer comes down to one word: control. Because this method gives scientists such precise atom-level control, they can build materials for some truly extraordinary things. We're talking about the super durable, scratch-proof coatings on your glasses, biocompatible materials for medical implants that your body won't reject,
or even hyper-efficient catalysts that make chemical reactions way faster. This is the science behind advanced sensors, electronics, and even better solar cells.
And that really brings us to the most important takeaway here, which is summed up perfectly on this slide. It is all about control. By carefully tweaking each of these 6 steps, the temperature, the ingredients, the timing, scientists can precisely decide the final structure, the size, and the properties of the material they want to create. This incredible level of control means we can literally design and build new materials to solve some of our biggest problems. And it leaves us with one really exciting question. If we can truly build our world one atom at a time, what are we going to build next?